Hey guys, Miss Marusik here, and in this video we're going to talk about stoichiometry calculations where we are converting with particles within a particular compound. Now, as a reminder, we've talked about three different types of particles up to this point. Atoms, which we use for particles of singular elements, molecules, which we use for particles of covalent compounds, and formula units, which we use for particles of ionic compounds. Now, here's kind of the awkward thing though. Within a covalent compound, within a molecule, or within a formula unit, within an ionic compound, there are atoms that exist inside of that. And so sometimes we need to convert between the compound as a whole and the atoms that are inside of it. And so we're going to see a new type of conversion that we could set up in order to achieve that goal. Now, before we do a calculation, I actually want to backtrack for just a minute and review something that we've talked about before, and that is our calculation heart chart. So if you have, say, an extra sheet of paper lying around, or if you want to use the back side of your notes, I want to review this because we're going to add a little bit to it today. So hopefully this looks familiar. We have our mole in the middle, and the joke is that the mole is the heart of chemistry, so I kind of think of that as being in the middle and the most important thing. And if I want to convert between moles and mass of an element or a compound, I would use the molar mass as a conversion, and that would allow me to convert into grams. However, when I set up that conversion, as a reminder, we always put 1 with moles. So 1 mole would be equal to the molar mass in grams of that substance. We can also go between moles and particles, our atoms, molecules, or formula units. And as a reminder, we see that molecules and formula units, we have some abbreviations we're allowed to use. And if I'm trying to go between moles and particles, the conversion that I would use in order to do that is our Avogadro's number, our 6.022 times 10 to the 23rd. And if I'm trying to go, say, all the way from particles 2 grams, then I could do 2 conversions. So I could do Avogadro's number to moles, then I could do molar mass to grams, or the other direction as well. What I want to do today is talk about how within this side over here with particles, we can do some extra things. If our particle happens to be a molecule or formula unit, so a compound, we can translate that information into or back and forth between atoms within. Say, for example, an atom that is inside of that compound. So I might have a whole entire molecule, but I want to discuss how many atoms are inside of that. And so to do that, what we're going to do is we're going to convert using a particle ratio. Now, I want to give you an example of a particle ratio so you know what in the heck that means. So let's talk about, for an example, water, which is H2O. If I think about having 1 molecule of water, I know for that 1 molecule of water, there are 2 hydrogen atoms inside of that. And so I could set a ratio where I say 1 molecule of H2O for every 2 atoms of hydrogen. Or, depending on where I needed those units to cancel, I could also say, hey, for every 2 atoms of hydrogen, that would be for 1 molecule of water. So you notice one of our big thing, and here being a molecule because water's covalent, one of our big thing has however many little atoms inside of it. Now, you could obviously also do this for oxygen. For oxygen, we would have 1 molecule of water for every 1 atom of oxygen, or you could say every 1 atom of oxygen is for 1 molecule of water. So that ratio is not quite as exciting because it's a 1-to-1. With the hydrogen, it ends up being a 2-to-1. The reason why we might want to flip this is because if I'm doing my dimensional analysis, remember I need my units to cancel out as I'm setting up my steps. And so depending on which direction I'm taking my calculation, I might need one or the other thing on the denominator in the bottom in order to get those units to cancel out. So So just keep in mind you can flip around those ratios. So with that said, let's talk about how we might solve a problem involving this. Now, one thing we do have to be really careful on when we're setting up these problems is that what we're going to see is that our how much or how many statement might be mentioning one substance, whereas the given information might be mentioning a different substance. For example, on this first one, it talks about how many nitrogen atoms, but then it talks about 45.8 grams of ammonium nitride. So you notice here we have nitrogen, here we have ammonium nitride. And whenever you see on a calculation like this that you're dealing with two different substances, please make sure you are always including what substance you have on each step. Do not get lazy on your units. And I'm going to tell you why. The biggest errors I see people make are misplacing things. And the reason why they're misplacing things in their conversion steps is because they're being lazy on their units and they're not taking the time to write what substance you have where. So just make sure you are not getting lazy on your units. I promise that's going to pay off for you. So let's talk about this one. I'm going to first start this off just like we started off all of our other calculations we've done with stoichiometry up to this point. I'm going to write how many nitrogen atoms. So I'm going to put atoms of N are equal to our start number, which is 45.8, and we have grams, and we see we have ammonium nitride. Now, here's where our formula writing is going to come into play. Hopefully we see how important that formula writing is going to be. I see I have ammonium, which is a polyion. Nitride, ending in "ide," would be a nonmetal. Polyion and a nonmetal would be ionic, so I need to worry about charge here. Ammonium is NH4 plus 1. Nitride is just simply nitrogen. And nitrogen has a -3 charge based on its group. So if I was to write these together in a compound, I would want to write my NH4 in parentheses with the 3 outside of it. We're going to need 3 of those to balance it out. And then we're going to have our N. So we can very clearly see here that I'm dealing with a compound and an element inside of it. And so what I want to do is kind of decide a game plan here to solve this problem. So I'm going to go consult my heart chart here. And I see that I'm dealing with the mass of our ammonium nitride. And I want to get to those atoms of nitrogen inside of it. So I'm going to have to go grams to moles using molar mass. I'm going to have to go moles to particles using Avogadro's. But that's going to be for that compound. Remember, here with the grams, I had ammonium nitride. So I'm still going to be in terms of ammonium nitride when I get over here to particles. So since ammonium nitride's ionic, our particles are going to be formula units. So then that's where I'm going to need that extra step of going from the ammonium nitride into just the nitrogen. So we're going to have to utilize this atoms within particle ratio conversion here. Okay, so with that said, let's kind of start stepping through our conversions. The first step I mentioned was that we're going to need a molar mass. And so as a reminder, I would bust out my periodic table and start calculating this. All right, so our ammonium nitride had a grand total of 4 nitrogens. So I would have my 14.01, 4 of those. And I would also add on my hydrogen at 1.01 apiece. Now that we had a grand total of 12 of those in there. And so that gets us a molar mass of 68.16. Now let's think about how we're going to use that. So we know we're going to have a molar mass step here. If grams of this ammonium nitride are here on the top, then remember we need that on the bottom. And so I'm going to put that 68.16 grams on the bottom for every 1 mole of that NH4,3N. So now here's where I can go from moles to particles. However, I'm still going to be in terms of that ammonium nitride, so I'm going to call those particles formula units since my substance is ionic. So another step here, moles of NH4,3N are going to go on bottom. We're going to take this into formula units of the NH4,3N. And as a reminder, again, with moles, I put 1. With my formula units, I'm going to put my Avogadro's number. Now, so far, this looks exactly like some of the calculations we've done in the past. There is nothing new here beyond what we've already done. Here's where our new step comes in. I need to get from, in terms of this compound here, this NH4,3N, into just the nitrogen that's inside of it. And so this is where our particle ratio comes into play. So if I had formula units of NH4,3N here, of course I would need that on the bottom. So again, notice that every step I am writing what substance I have where. That's to keep me straight on what should go where. Also, because I was in NH4,3N, that means all of this information's for the compound. So that molar mass needs to match up with the compound. Here's where we're going to make the transition between the formula units and the atoms of nitrogen that are inside of it. So here's where we say, hey, for every one of the overall compound that we wrote, so for every one formula unit, there are going to be a grand total of 3 plus 1, so 4 total atoms of nitrogen inside of it. So right here, this very last step is our new piece. It's our particle ratio where we're transitioning between the compound and the element inside of it. So now that I get all my units to cancel, so you notice that the grams of ammonium nitride cancel, moles of ammonium nitride cancel, formula units of ammonium nitride cancel. I'm now in terms of just atoms of nitrogen, so I'm ready to plug this into my calculator. Now, as a reminder, I like to plug these in exactly like they look. I think more people make less mistakes if they plug it in how it looks. So I'm going to put my 45.8 in, open parentheses, 1 over 68.16. Then I have my 6.022 E23 divided by 1, and then I'm going to have my 4 divided by 1. Now, obviously, this is going to get us a number here that has lots of digits. I don't want to have to show all those digits, so we can use our Sig Fig rules. 45.8 at the very beginning had 3 significant figures. Remember, constants and conversions don't count, so I'm going to show 3 significant figures here. That 8 would round up that 1, and so I'm going to report 1.62. Don't forget, though, with particles, you probably have a times 10 at the end of it. Remember, particles are really small, so you're going to have lots of those. So I'm going to report 1.62 times 10 to the 24th, and that's going to be in terms of atoms. And I'm going to go ahead and report that that would be for nitrogen. All right, let's go ahead and look at a second one. It says if there are 8.50 times 10 to the 25th atoms of chromium in a sample of sodium dichromate, how many grams of the sodium dichromate are present? All right, so yet again, I see, I'm given atoms of an element, and I'm being asked about grams of a compound. This time, though, the number that we know and the unknown are kind of flip-flopped. You notice that this time we know the atoms, but we are questioning or trying to figure out what the grams of the whole compound would be. So basically, what we're going to do is, if you're thinking about your map here, we are starting out with the atoms within, and we need to work back to the grams of the whole compound. So what that means is that this time that particle ratio is going to come first, then we're going to go particles to moles, and then moles to mass. So again, through here, we're going to be in terms of that compound, but right here is where we're going to transition from the atoms to the compound itself. And here, sodium dichromate, sodium's a metal, dichromate's a polyion. It's ionic, so again, our compound particles are going to be formula units. All right, so with that said, let me grab a different color here. All right, let's go ahead and write us a formula for sodium dichromate. Sodium is Na. It's in group 1, so it's going to have a positive 1 charge. Dichromate, as a reminder, is Cr2O7 -2. Dichromate's a weird one because it looks like it has a prefix on it, but remember the dichromate here, the di is actually part of the polyatomic ion name. So it's a little bit different than, say, our covalent prefixes. It's not a covalent prefix here. I notice my charges don't balance, so I am going to need 2 of those sodiums to balance it out. So coming down over here, I'm looking for how many grams of that Na2 Cr2O7 are there if we have 8.50 times 10 to the 25th atoms, and I'm going to specify that this is for Cr, for the chromium. Again, I notice these two substances right now, while related, are different, and so I want to make sure that at each and every step, I'm paying attention to where I have the compound and where I have the element inside of it. Okay, so with that said, we know our first step has to have atoms of chromium on the bottom because we need that to cancel, right? Okay, well, as we said, this is where we're going to go ahead and transition using our particle ratio into terms of the Na2Cr2O7. And I'm going to call those formula units because it's ionic. Now again, one of our big overall particle, one of our formula units, has 2 chromium atoms inside of it. So this is where it's very important to pay attention that the atoms were on the bottom, and so that's going to have how many of those atoms are inside one of that overall formula unit. So again, very important to put what units you have where. All right, so now that I'm in terms of formula units, now I can go formula units to moles and moles to our mass, to our grams, very easily using the same steps we're already familiar with. So if formula units was on top here, I'm going to put formula units on bottom here in the denominator. And as a reminder, we're going to moles in this step. So again, when I'm using our Avogadro's number to make this conversion, 1 goes with moles, Avogadro's number goes with particles. And then we're going to take that moles, squeeze it in over here. So I'll do this, mole of Na2Cr2O7. And we're going to take it into grams of Na2Cr2O7. All right, so this is where I would utilize our molar mass. I already have the molar mass calculated. It is 261.98 for this compound. If I'm thinking about where it would go, as a reminder, 1 goes with moles, so that 261.98 needs to go on top with the grams. So you notice we did a very similar calculation to what we did up above. It's just a matter of the order everything went in. While as here we were starting off with grams, the compound, that particle ratio came at the end. On this particular problem, I needed that particle ratio first so then I could get to grams at the end. So sometimes we just need to flip the order on all of those conversions. All right, so I'm going to go ahead and plug all of this in here. So I have, let me clear that. I have my 8.50 second e to the 25th. I have 1 over 2. I have 1 over 6.022 second e to the 23rd. and then I have my 261.98 divided by 1, which of course a divided by 1 doesn't do anything, but sometimes I like to just go ahead and plug it in anyway, can't hurt. Now obviously I don't want to show all of these digits, that would be ridiculous, so I want to round using significant figures. I notice my initial number has 3 sig figs. Now be really careful here. I know we thinking, oh hey, that 8 would round up to 4, but you cannot simply just write here 185. Why? Because this wasn't in the hundreds, this was in the 10,000s. So what we can do is put 2 zeros as placeholders at the end of that. The other option is to put this into scientific notation. So you could also report 1.85, and that would move that decimal over 4 places, so you could put times 10 to the 4th. Our unit here would be grams of the Na2Cr2O7. All right, so here's the deal. On the next page, there are 2 more problems. So let me put them up here. All right, so here's what I want you to do. I want you to pause the video and take a couple minutes and see if you can solve these 2 problems, and then I'll put the answers up here in just a moment. So go ahead, pause the video, try them out. Okay, did you pause it? I hope you tried them out. Okay, let's look at some answers here. You got to see one each direction here again. So on the example 3, it asked how many carbon atoms are there in 16 grams of glucose. So that means I was starting off with the mass of the whole compound. So I did mass to moles using molar mass. I did moles to molecules using Avogadro's number. Now I did call it molecules here because glucose is covalent, but basically it's very similar to formula units for something that's ionic. It's basically the equivalent of that. So then, just like we saw a moment ago, I can go from molecules into atoms, saying one of the overall molecule, one of the big thing, has 6 atoms of carbon inside of it. Again, that's just coming from that subscript. All right, on the next problem, example 4, if a sample of aluminum sulfite had 4.55 times 10 to the 23rd atoms, and here they clarified that they might have called them ions of aluminum, you would do it the same way, and wanted the mass of the entire sample. So I started off with my atoms of aluminum here, and in order to get to the full compound, I first did the particle ratio at the beginning, so 2 atoms of aluminum for every 1 formula unit of the aluminum sulfite. Then I did my Avogadro's number, 6.022 times 10 to the 23rd formula units for every 1 mole of that overall compound. And then I did my 1 mole is 294.14, so there's my molar mass step. So again, my particle ratio, my Avogadro's number step, and my molar mass step. I want to kind of mention here, hopefully we've figured out that formula writing is really, really, really important. Obviously, on all of these examples, if you wrote the incorrect formula here for your ionic compound, think about all of the things that would be affected. You would have the wrong number of atoms here, okay? You would also have the wrong molar mass. So formula writing is extremely important in order to be able to get these calculations correct. You can know how to do these calculations all day long, but if you can't write the correct formula, they're not going to come out right for you. So just be very careful with that. All right, I hope we're feeling good about calculating between particles within and a whole compound, setting up a particle ratio conversion. If you have any questions or need any help, please feel free to email me. Bye, guys.